using two different bonds. En. We are usually simply drawing using En and two bonds. So this is the cis isomer because they are on the same side. En are on the same side and also Cl are on the same side. So this is cis. What is the name of this? This is di. Because it is a di-dentate ligand, instead of di we are using bis. So bis ethylene diamine. First in alphabetic order, first chlorine will come. Dichloro bis ethylene diamine cobalt 2. Dichloro bis ethylene diamine cobalt 2. Then we can draw the trans isomer also. This is a trans isomer inside here because the same ligands are on the opposite side. So this is an example for Ma, AA2, B2 complexes. So that are the two type of geometrical isomerism. Then another type of geometrical isomerism is shown by complexes of the formula Ma3B3. It is also an octahedral complex because the number of ligands will be 6. Can draw two because look at these pictures. Here the same ligands, that is AAA, or you can select BB. Here I selected only A. You can select either A or B. Here A type of ligands are aligned at the same plane, same triangular plane of the octahedron. Same face of the triangular face. You can imagine an octahedron with eight faces. These three ligands are come at the same face, same triangular face. So it is called facial, same face. So it is called facial or it is called FAC isomer. Here the same ligands are come at the meridian. You can draw a diagonal in the middle of the complexes. So it is come at the median triangular median of the octahedron. So it is called the mer isomer, or in the meaning of meridian. So it is called the meridional isomer. So Ma3B3 are showing two type of isomerism, that is FAC isomerism and mer isomerism. In FAC isomerism, same type of ligands lie on the triangular face of the octahedron. That is why it is called facial, same phase, facial or FAC isomer. In this isomer, the same type of ligands are lie on the diagonal triangular face of the, in median of the octahedron. So it is called a mer isomer, or the full form is meridional isomer. So these are the examples we can discuss in geometrical isomerism. Ma2B2, and then Ma4B2, MAA-B2, then Ma3B3. In this case, we are using FAC and mer isomer instead of geometrical isomers. Then next we will go to the last type of isomerism, last type of stereoisomerism, that is called optical isomerism. So before going to learn about optical isomerism in complexes, let us discuss the optical isomerism in what is meant by optical isomerism. I know that you already learned that in organic chemistry, but I will discuss that first, then only we will go to the example. Optical isomerism is a phenomenon of, or it is the ability of some compounds, maybe that is in organic or inorganic, to rotate the plane of plane polarized light either towards right or towards left. That is, some compounds, compound solution. When we pass plane polarized light is produced by passing normal light to a Nicol prism. Plane polarized light has only one vibration, they vibrate only in one plane. When plane polarized light is passed through solution of some compounds, they will rotate. This is the axial plane of vibration, that either towards right, that is the angle of rotation, or towards left. So there is change in the wavelength of light we passed. So this is called the optical activity. If it is rotating towards right, they are called dextroisomers and represented by D. And if it is rotating towards left, it is called levoisomers represented by L. Then these two isomers are together called enantiomers. So optical isomerism is a phenomenon of rotation of plane polarized light either towards right or towards left. If they are rotating towards right, that type of isomers are called dextro, and if they are rotating towards left, that type of isomers are called levo. These two isomers will be mirror images and they are called enantiomers. Then for exhibit optical isomerism, the compound should possess some structural features. First one, it should be non-superimposable. Non-superimposable means take an object and take its mirror image and we are keeping one above the other. If it is imposing, that is not optically active. But if it is not same, that is called a non-superimposable. That type of compounds. That is, if a compound possesses a non-superimposable mirror image, that compound is called achiral, and it will it will called chiral and it will show optical activity. We'll discuss an example. For example, I'll write a letter. For example, A. If we take the mirror images are showing represented like this. We'll take the same. Then take this A and keep above this A. They are superimposable. That means they are not optically active. That means they are achiral. Otherwise, take another letter and take this mirror image. Then if you are keeping above this is the original and this is the. They are non-superimposable. That means it is chiral, and this type of compound will be optically active. So, coordination complex with this type of structural, that means if they possess non-superimposable mirror image, they can rotate the plane of plane polarized light either towards right or towards left, or they are called achiral and they are called chiral, and they can exhibit optical activity, and these two isomers are called enantiomers. So enantiomers are non-superimposable mirror images of an optically active compound is called enantiomers. Let's consider an example. COEN twice Cl2. It's an octahedral complex. 2 into 2, it is a didentate. 2 into 2, 4. 4 plus 2, 6. This is an example. Draw its mirror image. Mirror image is the image we obtain when we look through a mirror. This is the mirror image. Is it superimposable? We can check. Take this and keep it here. What happens? We know that one Cl will come here, then one En will come here. So it is non-superimposable. That means they are chiral. That means they are optically active. And these two are called enantiomers. If it rotates, if it is dextro, it will be levo. If it is levo, it will be dextro. Then another example. So we can draw another isomer of this same, which are not superimposable, which are not optically active. CO, Cl, Cl, En, En. Mirror image, the same will come. Cl, Cl, En, 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 En. If you take this and keep it on this, Cl will emboss with this Cl will emboss with this En will emboss with this En will emboss with this. That means they are not superimposed, but they are impossible. So they are achiral. It is not optically active. So using this same structure we can draw 4 different structures. These two are optically active and these two are optically inactive. So for a compound should be optically active, it should possess a non-superimposable mirror image. That is a very important condition. Then we can draw another example. CrEn thrice, 3 into 2, 6. It is also an octahedral complexes. Draw the mirror image. Only get this EN will come here. This EN will come here and here. Take this and keep it above this. And it is also non-superimposable. So it is optically active. So that's all about isomerism exhibited by coordination compounds.